map, and companies are using it and proudly advertising that they're using differential privacy. And a lot of the credit goes to Aaron, who got in this as a postdoc, I believe. Is that right?
It was my PhD thesis.
Your PhD thesis, okay. And so yeah, he's been there from the beginning, and you'll hear about the latest bit.
All right, thank you. And yeah, thanks for having me here at Princeton. It's always a pleasure. So I'm going to talk about some recent work of mine together with my current student, Seth, and my former student, Stephen, who's now a professor at Minnesota. And I'm not going to assume that anyone here is an expert in differential privacy, although, you know, like just for entertainment, raise your hand if you know what the definition of differential privacy is. Okay, a couple of people.
Oh, if you know.
If you do know, raise your hand. Good. So I'm not assuming.
It's more than a couple, yeah.
Not assuming that you know. I sort of want to start with a crash course in differential privacy. You know, one can teach like a longer course in it, but this will hopefully suffice for the talk. So, first of all, the definition. What is differential privacy? There's a long history of studying different sort of mostly broken syntactic definitions of privacy in the computer science literature. You know, you've come up with some definition. The thing you're going to publish on the web either is or isn't private according to this definition. That kind of definition tends not to work, and there's a long history of sort of back and forth between people proposing new definitions and showing easy ways to break them. But in 2006, 2005, there was sort of a real breakthrough in thinking about privacy as a, giving a sort of meaningful semantic definition for what privacy means as a function of the process by which inputs are mapped to outputs. So the general idea is that privacy should be about protecting against arbitrary inferences made as a result of your data, not inferences made about your data. Okay, so it might be that I mistakenly believed that everyone has 2 left feet, and I do a statistical analysis and I find almost everyone has 1 left foot and 1 right foot, and therefore my beliefs about you in particular have changed quite a lot. The idea behind differential privacy is not to call that a violation of your privacy, because although it's an inference about your data, it's not one that I needed your data to make. I could have made that inference without having looked at your data set. Okay, so sort of the key idea in differential privacy is to separate out inferences about your data from inferences made because of your data. And the way it tries to do that is it says that an analysis of a data set is private if the data analyst can be proven to know almost no more about any particular person, say Alice, after the analysis is done, compared to what he would have known in sort of the counterfactual experiment had he still conducted the same data analysis, but on the data set in which Alice's data had been removed. Okay, so he might learn something about you, but only something that he could have learned even in the absence of your data. Okay, so more formally, and this is a definition that goes back to a beautiful paper by Dwork, McSherry, Nissim, and Smith in 2006. Differential privacy is going to be some property of an algorithm. An algorithm is just some randomized mapping between sets of records, multi-sets of records, to some distribution over outputs. And differential privacy will be some Lipschitz condition on this mapping. So it says, if I change the input by only a little bit in, say, Hamming distance, I change like 1 record of the input, that should result in some change in the output distribution that should also be small according to some metric. Okay? So to define differential privacy, there's this notion of neighboring data sets. These are typically thought of as 2 data sets that differ in a single record. So consider, like the data set as it is, which includes your record, and the data set, that's data set D. And then there's data set D prime, which is identical to data set D, but in which your record has been removed. Okay, so we're sort of comparing what happens in the world in which we allow your data to be used in the analysis and the counterfactual world in which we do not. And we say that an algorithm is differentially private, and differential privacy comes with 2 parameters, epsilon and delta, which quantify the strength of the guarantee. If I can promise that for all pairs of neighboring data sets and for all for all outcomes that might result from the analysis X, the probability that that outcome occurs should be similar whether the algorithm was run with your data or without it. And here similar means within a e to the epsilon multiplicative factor, and think of epsilon as a small constant, so read that as 1 plus epsilon, and maybe within a delta additive term. Okay, think of delta as something pretty small. Okay. So that's the mathematical definition. It's some Lipschitz constraint on mappings from data sets to distributions on outputs. So this is a nice definition for a number of reasons, and I'm not going to go into all of them because I want to sort of get to the results that are the focus of this talk. But let me tell you a couple of sort of important properties that this definition has. Basic but important properties. So one is it satisfies something that's a lot like a data processing inequality. It's closed under post-processing, which means that if I've got some algorithm M, and I promise you it's differentially private, and then we consider the algorithm that we get when we apply some arbitrary function f to the output of M, okay? Even though I don't know what f is, I can be confident that f of M is also differentially private with privacy parameters that are the same or better. Okay, so I can't, by thinking about the output of your mechanism, somehow make it less private. Okay, that's important for two reasons. So first of all, it's important just when you're doing algorithm design. It means that you can treat, like differentially private subroutines as little modules, and if you've proven the privacy guarantees of them, you don't have to worry that you're going to ruin them by, post-processing the output. But it's also useful when interpreting the definition. Okay, so here's just the definition of differential privacy again. And it's really talking about outputs like X in the range of this mechanism M. Right, and if M is doing some complicated statistical analysis or even a simple one, it's just releasing, like coefficients of a linear regression, it's not obvious why you would care about particular outputs. Like you might not have strong preferences over the regression coefficients on different features. But there are things in the world that you do care about. Okay, like you care about whether you're denied health insurance. And to the extent that the output of this study is related to those events in any way, like maybe if we discover that smoking and lung cancer are correlated, the health insurance rates will increase for smokers. To the extent in which the outputs of this study are related to events you care about in any way, they're related via some relationship that I can encapsulate as some post-processing function f. Of course, I don't know what that function f looks like, but I don't need to. And so what the post-processing guarantee means is you can literally take this definition to be promising you that no matter what it is you're worried about, maybe being re-identified in the data set or having your health insurance claim denied or getting annoying phone calls during dinner, like simultaneously for everyone, no matter what events they're worried about, what this promise means is that the risk of those events will increase by only a bounded amount, hopefully a small bounded amount, by the result of their decision to allow their data to be used in the computation. Okay, so it's a strong safety guarantee. It's promising no matter what you're worried about, that thing won't become much more likely if you allow your data to be used. Okay, so that's one of the sort of strong semantic meanings of differential privacy. Okay.
But I guess maybe it should be pointed out that it's kind of like one of these Nash equilibria, or sort of one of those kinds of things that everybody else's decisions are given.
That's right.
Something is going to become public anyway.
Exactly, yeah.
And this is only your marginal.
That's right. So in some sense, it's a very utilitarian definition. Like, to the extent that your power is to just unilaterally withhold your data, this is motivating you to do it. It's saying you're no worse off if you unilaterally sort of provide your data. Of course, you might be like way worse off because I ran this study.
And you may get the telemarketers anyway.
That's right. But in some sense, this is also sort of the strongest kind of definition you could hope for while allowing statistical inference. Because if you wanted to promise that you would come to no harm as a result of the study being carried out, well, you can always cook up situations in which I learned some population-wide correlation that, from publicly observable data about you causes me to update my beliefs a lot in a way that harms you. For example, if I learn that smoking and lung cancer are correlated and you're known to be a smoker, your health insurance rates might go up. And if you wanted to try to rule that kind of thing out, you'd have to prohibit learning any correlations at all from the data. So yes, this doesn't promise you freedom from harm. It promises you freedom from additional harm as the result of the use of your data. But it's also consistent with doing science. And anything that's consistent with doing science, meaning learning any correlations at all from the data, might cause you to be meaningfully worse off, like in the world in which the study was carried out compared to when it wasn't. So you sort of have to relax that. Good question. Okay, one additional useful basic property is that you can treat differentially private algorithm design as modular. So if I have a bunch of little subroutines that are sort of each pretty simple and I've proven them to be differentially private, then I can glue them together in arbitrary ways, and the outcome will also be differentially private with parameters that degrade in a sort of predictable way. Okay, so I don't have to, and this is sort of important, right? I can design complicated algorithms, but I don't have to analyze each one from scratch. You can sort of build up a collection of tools. Okay. Okay. So good definition. It would only be, it's not interesting, of course, if you can't do anything useful under this definition. And fortunately, there's lots of things you can do subject to differential privacy. There's a sense in which differential privacy is really compatible with any kind of statistical data analysis task. Anything whose answer is definable based on the data distribution and not based on, the particular sample of data you have. And so you can solve machine learning problems, all of, pack learning, for example, anything that's privately pack learnable, okay, with some caveats. Anything that's privately pack learnable over anything that's pack learnable over a finite data universe is privately pack learnable as well. There are some differences when you move to infinite data universes. So for any epsilon and delta, the question will ultimately be how much larger will your sample complexity be? So these things don't come for free. In general, to solve these private learning problems, there will be some overhead on the order of something like 1 over epsilon times log of the data universe size to solve them privately.
But the algorithms remain efficient?
Not necessarily. So that's going to be one of the things we talk about today. Yeah. In fact, on the next slide. So, right. So these are all information theoretic results saying there's lots of stuff you can do. Like you can do machine learning. You can do, in fact, synthetic data generation. So suppose I'd like to share my data set to allow other people to do machine learning. I'd like the data set I share to be consistent with, exponentially many or infinitely many classes of statistical queries or empirical risk minimization problems. You can do that too. You can do these things even if the questions you want to ask are not known to you ahead of time, even if they arrive online and are adaptively chosen. And in fact, that's useful beyond differential privacy, because it turns out that differentially private algorithms cannot overfit. And so the fact that you can answer queries adaptively by reusing the same data set provides the best known methods we have now for reusing data for statistical analysis tasks, even if you don't care about privacy. Okay? Okay. But there's a substantial caveat, which is that in general, computational efficiency is not preserved under these reductions. So all of these problems, at least in their most general forms, are known to be hard. Okay? They're known to be hard, subject to various cryptographic assumptions. So okay.
To be hard, assuming that you know how to solve the pack learning problem efficiently, still how to do it.
That'll be what we talk about today. So, okay, so pack learning is hard in the worst case, even without privacy. Synthetic data generation is trivial without privacy. I could just give you my data set, but that becomes hard when I introduce privacy. And similarly, answering statistical queries, which isn't hard without privacy, becomes hard with privacy. And in fact, even without privacy, if I wanted to answer these statistical queries adaptively in a way that wasn't just accurate in sample, but was accurate out of sample, that becomes computationally hard as well. So information theoretically, there's lots of stuff you can do, but there are sort of serious computational hardness results which get in the way of practical adoption of many of these in principle possible things. Okay. Okay. So, okay, so like there's pervasive computational hardness. And one question is, what should we do with this? How do we proceed? And the situation is not so dissimilar from the state of affairs in machine learning, in that if you look at like the pack learning literature, even the very most basic learning problems, learning half spaces, are computationally hard. They're hard even to approximate. Okay? But that doesn't seem to have stopped machine learning. I mean, we solve linear classification problems all the time. We have for many years. This is the problem that support vector machines solve, the problem that logistic regression solves. And we solve much harder learning problems as well. Somehow it seems like this worst case hardness hasn't meaningfully impacted the practice of machine learning. We've got, right, this is in part because, you know, problems that are hard in the worst case can be solvable in practice with lots of heuristics that have been developed over the decades. So from simple things like logistic regression and support vector machines to sort of, you know, okay, stochastic gradient descent to more sophisticated tools like, you know, you can download Gurobi, and it turns out you can solve giant like integer programs, even though that's like a canonical NP-hard problem. You can solve giant SAT instances. There's been sort of decades of research effort into developing really optimized heuristics for solving hard problems. Okay, so hardness, like worst case hardness, doesn't necessarily stop us from solving problems. Okay, but differential privacy is a little bit different. So in machine learning, like you typically like have like a goal, which is, you know, like empirical accuracy or something. So you can pick your favorite heuristic, you can, you know, develop a new algorithm. You don't necessarily need to prove anything about it, right? Like it's fun to think about proving why we can train neural networks, but you don't need to do that to train a neural network. You can just go and see if it works, and you can evaluate the accuracy. Okay? Yes?
So if you have a convex machine learning problem, you have a convex decision set, a convex loss function, can you then have a differentially private?
Yes, we can solve convex ERM problems subject to differential privacy.
So that kind of captures most of what you would want.
It captures...
and there's some Lipschitzness, right? Very strong Lipschitzness.
So you need the gradients to be bounded. So basically, like stochastic gradient descent is already robust to noise. So you know, you can like run stochastic gradient descent and add Gaussian noise, and now it's private, and it sort of does the same thing. Yeah, so that solves, you know, a lot of convex ERM problems. It doesn't get you all of the way there for like synthetic data generation, but that's true. You can do that. Okay. So like, you know, like accuracy is empirically verifiable, but this definition of differential privacy, it's got all of these universal quantifiers. So you can't just like check if your algorithm is differentially private, right? Like that's sort of a worst case definition that requires a proof. Okay. So the sort of starting point for this work is to try to think about how to develop a theory for using heuristics to solve these hard problems in data privacy, where maybe we're willing to assume that, you know, like when proving that our algorithms do something useful, we're willing to like assume that our heuristics work. But when proving that our algorithms are private, we really would like to not have to assume that. We'd like to prove privacy in the worst case. Okay. Okay. So let's write down some notation. I'm going to talk about two kinds of problems, learning and query release, but I can talk about them mostly with the same set of notation. Okay, so our data universe is going to be called X. That just means our data set, whatever it is, will be a collection of records from X. Okay, maybe, you know, X could sort of be anything, but maybe to sort of keep it something concrete in your mind, think about the Boolean hypercube. So, you know, the entries in your data set are vectors consisting of D Boolean features. We'll also be talking about classes of functions. These are just arbitrary functions mapping from X to, let's say, some binary classification, +1 or -1. Okay, so think about linear threshold functions or conjunctions or decision trees. And it'll be useful to talk about two different kinds of data sets, unweighted and weighted data sets, which you can also think of as labeled or unlabeled data sets. Okay, because for learning problems, we care about labels, but for synthetic data problems, we don't. So an unweighted data set is just a collection of n records from the data universe. And a weighted data set is just a collection of n pairs, each of which is a record from the data universe and some real valued weight. Okay, and maybe think about the weights as encoding labels in a learning problem. So in a classification problem, the weights might be -1 or 1, specifying whether it's a positive example or a negative example. Okay, so we can define learning and optimization problems now. Okay, so a learning problem over a class of function C is just the following. Given a weighted data set, find the function in the class that maximizes the classification accuracy. Okay, so it maximizes the agreement of the function applied to the data point and the label. Or the labels are +1, -1, so we can, get this agreement just by multiplying them together. Okay, so that's the optimization problem. And the synthetic data generation problem is a little different. We're now given an unweighted data set. Okay, just a collection of n records. The thing that we want to output is also a collection of n records, like something else that looks like a data set. And what we would like is that for every function in our class C, of which there might be many, that when I evaluate the function on my real data set, which just take the empirical average of the function, it should agree approximately with the value of that function on the synthetic data set. So if you only care about functions in this class C, the synthetic data set is as good as the real data set, up to whatever error this squiggly line implies. Okay, those are the two problems I want to talk about. Okay, and in general, these problems are going to be hard, so I want to talk about oracles that can solve these problems. Okay, so a weighted optimization oracle is just like a subroutine that I might assume I have access to, which can in unit time solve the learning problem, solve the optimization problem. Okay, I give it a weighted data set, it spits back to me the function that best classifies that data set. Okay, now ultimately, I don't have oracles. I'll have heuristic oracles, which are just arbitrary functions. They purport to be oracles, but probably they're not. They're going to output any function in the class C. And playing a special role in what I'm going to talk about are what I'm going to call certifiable heuristic oracles. These are oracles that might fail to solve the problem that I give it, but I will know when they fail. Okay, so these are oracles that either will output the correct solution, the value of the the actual optimal solution, or they will say, I give up, problem was too hard, can't do it.
Wait, what is this? Do these exist?
Yeah, integer programming solvers. So any oracle, for example, an NP decision problem, or more relevantly for us,
sound procedures.
That's right. So things like branch and bound and cutting planes methods. Like if you download Gurobi and you give it an integer program, there are two things it could do. Like you can always set a timeout and it'll give you the best solution it's found so far. But if it runs to completion, it'll come with a certificate proving that the solution it found is actually optimal. So I think integer programming solvers are the best example for what I want to call, like a certifiable oracle, but stat solvers are certifiable as well because you can check. But unfortunately, things like backpropagation and logistic regression are not. Yes, so definitely the set of certifiable heuristic oracles is limited. A lot of the heuristics you'd like to use are not certifiable, but it's not empty. You can download Gurobi and have a certifiable oracle.
Why did you use a new term rather than just sound or something?
A new word. Yeah, I guess sound would have been a good word. That's all I mean. Okay. So now some definitions for the kinds of objects we'd like to produce. So I could say that an algorithm which has access to an oracle is oracle efficient and differentially private if, assuming access to the oracle, it's a polynomial time algorithm and it's differentially private. But crucially here, the proof of differential privacy might assume that the oracle actually works, that you really have access to the oracle. A better guarantee is if I could say that the oracle was robustly differentially private. And by that I mean an algorithm whose proof of privacy does not depend on the correctness of the oracle. Okay.
Sorry, the last one.
Okay, so it's going to be robustly differentially private. I should still prove things, like I can still assume that the oracle works when I'm proving that the thing, runs in polynomial time, or when I'm proving that the thing like gives a useful answer. But when I like sit down to prove that the thing is differentially private, I shouldn't rely on the fact that like the oracle you gave me was a real oracle. Unlike in this first definition, when I'm allowed to. Make sense? Okay.
But you don't know anything about this oracle, so it could do whatever it wants with the data.
That's right. Although
something like
the results I'm going to give are going to be for certifiable oracles, but they could, like otherwise I don't know anything about them. They could fail in adversarially chosen ways, which is the challenge. Okay, so let me tell you what we can show, and then I'll in the remaining time, try to show you a little bit about how we do it. So first of all, first result for learning. Okay, so there's some large class of functions that satisfy some property that I'll tell you about in a few slides, but it includes a lot of your favorite, maybe discrete concept classes from pack learning theory. So conjunctions, disjunctions, discrete linear threshold functions, parities, decision lists. Okay, like think classic pack learning theory concept classes. So there's some large class of functions for which there are oracle efficient differentially private learning algorithms. Okay, yeah.
So if I have an algorithm for synthetic data generation for any of these problems, then it is immediate that I will also have the Auricle differentially private algorithms, right? Because basically any algorithm I could apply to the synthetic data would basically be private.
That's right. Synthetic data generation is a harder problem in that sense than learning, because you can always then do your learning on the synthetic data. That's true. So yeah, we're going to try to get synthetic data generation algorithms from the, we're going to try to go in the other direction. You give me an oracle for learning, I solve synthetic data generation. Okay, so for a large class of functions, you can get oracle efficient differentially private algorithms. I didn't say robustly here, so the proof of privacy here requires that the algorithm actually, the oracle actually work. Okay, and you also pay something in accuracy. Our oracle efficient algorithms are not quite as accurate as sort of the best known information theoretic algorithms absent a sort of efficiency requirement. Okay. Second, if you give me an oracle efficient differentially private algorithm, and the oracle you instantiate it with is a certifiable oracle, meaning it can fail, but I know when it fails. Okay, so like an integer programming solver that works for your family of problems. Then there's a generic reduction that if I'm willing to relax my privacy guarantee from epsilon 0 differential privacy to epsilon delta differential privacy, where delta can be as small as 1 over polynomial in n, because the running time is going to involve a 1 over delta term, then I can sort of generically take your oracle efficient private algorithm and make it robustly private. So turn it into something whose privacy guarantee does not require that the oracle work. And then for, again, a large class of functions that I'll tell you about, there are, by using these first two tools, robustly differentially private oracle efficient algorithms for generating synthetic data for these functions. Okay, so you can solve not just the learning problem, but the synthetic data generation problem. Okay, so if you have, if you find that for learning conjunctions, say, Garobi is able to solve the corresponding optimization problem, then you can go through this chain of reductions and have a polynomial time algorithm that will make calls to Garobi and will generate for you a synthetic data set that is consistent with yours for all of the 2 to the d conjunctions. Okay, this is the set of results. Before I sort of go further, are there questions just about the meaning of these claims? Yeah.
So I just want to confirm that I understand 3 correctly. If I had a differentially private synthetic data generation algorithm, then I have, with respect to a certain set of queries, then I would be able to answer those queries privately just with the synthetic data, right?
So if you wanted to solve the learning problem, you'd still need some non-private way of solving it on the synthetic data. So you'd still need like an Auricle for the learning problem, but you could apply it to the synthetic data, so you wouldn't need sort of a private learning algorithm.
Right. So then
But information theoretically, synthetic data generation is a harder problem than learning.
So I guess maybe I'm worried that there is no utility guarantee in 3.
All of these have utility guarantees, assuming the Auricle works. So you know, like good synthetic data. I'll tell you the parameters as we go on. But yeah, I mean like, yeah, I mean I guess like the way I defined things, you know, there's, I could have made these statements like in bad faith. They'd all sort of be vacuously true with giant error parameters, but like implicitly, with you know, like there are utility guarantees as well. Thank you for that question. Yes.
So can you just clarify the Oracle efficient differentially private algorithms in 2 includes, like it's really any kind of algorithm? So for instance, 3 is a corollary of you can design one that is differentially private and then just plug into 2 and that's how you get 3?
There's something else, although it's sort of, there's not a lot of new ideas to get 3. So when you get 1 and 2, now you've got these robustly private learners, which can sort of serve as a separation oracle for, you know, like an optimization problem. So there's some stuff to do, you know, there's some primal dual algorithm here, but like, you know, if you're familiar with the synthetic data generation literature in differential privacy, once you have 1 and 2, 3 wouldn't surprise you. But you have to like call the oracle, you have to call the learner you know, like built in steps 1 and 2 a bunch of times, you know, like in some kind of primal dual algorithm to solve a giant linear program, basically.
Okay. So you're saying so 2 really more applies to the kinds of algorithms you would design in 1, not 2.
So typically, like
directly for 3.
Yeah, I mean 2 is a generic reduction. You could, I guess you'd have a choice for how to like get to 3. You could sort of, from 1, design, you know, like a private but not robustly private synthetic data generation algorithm and then plug it into 2. But more efficient would be to do it the other way around. But 2 is quite general. Other questions about the nature of the claimed results? Okay. So before I get into the details, a couple of questions you might ask. So I said you can do this for like some yet to be defined large class of learning problems. You could ask, might there be Oracle efficient differentially private learning algorithms for all classes C known to be learnable? And the answer is no, because it turns out there are separations between what you can learn subject to differential privacy and what you can learn without the privacy constraint, just information theoretic separations. So even intervals over the, you know, like real line, which have VC dimension 1 and are sort of trivial to learn, absent privacy guarantees just can't be learned subject to differential privacy. For information theoretic reasons, not computational reasons. And so you can't have a sort of reduction from a non-private learner to a private learner that doesn't use any structure of the class, because private learning is different than non-private learning. Yeah, that's a good question too. So could it be that there are Oracle efficient differentially private learners for everything that's known to be privately learnable information theoretically? And potentially, we can't prove that's not the case. Right? That's like the main open question. Like maybe the power of Oracle efficient private learning is equal to the power of private learning, but you'd need different techniques. So there's sort of a barrier result that I'll talk about at the end, which basically reduces to a like hardness result of ELADS for Oracle efficient no regret learning. It turns out like lots of differentially private learning algorithms are really no regret learning algorithms in disguise. And we know, because of ELAD's work, that there are separations between what you can sort of learn in the no regret framework with Oracle efficient algorithms versus arbitrary algorithms. And so there's an interesting structural question, you know, are all differentially private learning algorithms, can they be converted to online learning algorithms in an efficient way? Like, so if I have an Oracle efficient algorithm for private learning, can I turn that into an Oracle efficient algorithm for online learning? Yeah, so I'll get to that at the end, but basically like, yeah, there's a large class of algorithms in the privacy literature. In that class are the things I'm going to describe. And any of those algorithms can be proven to have a regret bound in the online learning setting against an adversary, basically because they look like variants of follow the perturbed leader. Not all algorithms are in this class, which is why this is a barrier result, not a straightforward impossibility result. But one might conjecture that there's nevertheless a way to convert any private algorithm into a online learning algorithm with no blow up in running time, which would turn this into a real impossibility result. Okay. So but this is an interesting question. Like, we use one relatively restrictive kind of structure on the query class to get these results, but maybe you don't need it. Like, maybe everything that's privately learnable is privately learnable in an Auricle efficient way, but I would guess that it's not. Okay. Okay. So let me now sort of since many of you are unfamiliar with differential privacy, try to get to like our first result via like a series of warm-ups. Let me show you how to prove that like the sort of classical mechanisms in differential privacy are private, and then we'll build up to a simple mechanism that is private and Auricle efficient. Okay, so maybe the most basic mechanism in differential privacy for answering like numeric valued queries is the following. I'll just compute the answer and I'll add noise. Okay, the noise will be drawn from the Laplace distribution. Okay, if you don't remember what that is, I'll tell you the only thing you need to know about it. But basically, if I've got some question, numeric valued question I'd like to ask about my data set, which is of the form, like, what is the average of some function f of the data set? So like, here's some model. What's its error rate on the data set? Then one way I can answer that is by computing that number and perturbing it with noise from the Laplace distribution that has standard deviation that looks something like 1 over epsilon times n. Okay, 1 over n is sort of the scale at which you need to add noise, because if I change one element of the data set, it'll change this number by 1 over n, and so I sort of need to hide changes on the order of 1 over n. Okay, this is differentially private, epsilon differentially private. Why? Well, let's consider what would happen on two neighboring data sets, d and d prime. Okay? The value of this function f can differ by at most 1 over n on the neighboring data sets. That's sort of the worst case. So let's imagine for now that that really happened, that f of d is f of d prime plus 1 over n. And now let's sort of consider a coupling, if you like. Let's imagine I run the Laplace mechanism on d, I run the Laplace mechanism on d prime, and let's give a name to the random variables of the perturbations that I'm adding to these things. The noise I'm adding in the first run is z, the noise I'm adding in the second run is z prime. And the observation is, well, f of d is f of d prime plus 1 over n, so the outcome of these two mechanisms is exactly the same, exactly when z prime is z plus 1 over n. The noise has to be large enough by 1 over n to hide this difference in the function value. And the reason the Laplace mechanism was the right choice is because it has the property that when you look at the probability density function of the Laplace mechanism at any point x and compare it to the density at x plus 1 over n, no matter what x is, the ratio of those probability densities is e to the epsilon. Okay, when you use this parameter, that's what we need for differential privacy. Okay, so that's privacy of the Laplace mechanism, if you like, sort of by constructing the right coupling. Here the coupling was very easy to construct. Okay, suppose I want to do something more complicated. Suppose I want to actually not just evaluate the error of a single model, which is what the Laplace mechanism did, but I would like to solve the learning problem. I'd like to find the model, say in this case, I guess, with the highest accuracy. Okay, this is another classical mechanism, not ours. Okay, here's what I can do. I'll just compute the error of every model in my class, the accuracy of every model in my class. Just as before, I will perturb that accuracy with Laplace noise. Okay, now with scale 2 over epsilon n instead of 1 over epsilon n, so double the standard deviation. And then I won't output all of these numbers. That would be really bad, right? Because the privacy parameter, remember, composes linearly in the number of times I run a subroutine. So if the Laplace mechanism was epsilon differentially private, and I've got 2 to the d functions in my class, if I released all of these numbers, all I could say was that it was 2 to the d epsilon differentially private. That would be really bad. But I'm not going to do that. I'm just going to release the identity of the function whose noisy accuracy was largest. Okay, just release the sort of argmax. Okay, that too is epsilon differentially private. Let's think about why. Well, again, consider any function f star. Okay, let's give it a name, f star. On 2 neighboring data sets, I know that f star of d can differ from f star of d prime by at most 1 over n, because all of these functions are just the average of n numbers. Okay. In fact, for all of these functions f, right, for all of them simultaneously, when I look at their evaluations on d and d prime, they differ at most 1 over n. Okay. So now I sort of want to define basically the right coupling on the noise, so that if f star is output when I run the algorithm on d, under this coupling, f star will still be output when I run the algorithm on d prime. Okay. So let's consider some vector of perturbations, 1 for every function in my class. In the index corresponding to f star, I'll want to sort of shift the noise up by 2 over n. And I'll just leave it as it is in every other coordinate. So then the claim is that if on database D, the argmax of these noisy accuracy scores was f star, then on database D prime, the argmax of these noisy accuracy scores will also be f star when the coupled noise was z plus e. We shifted up the sort of noise added to f star and left everything else alone. Right? And that's just because, well, at sort of noise level z, f star was the argmax. When we moved to d prime, in the worst case, the value of f star went down by 1 over n. The value of everything else went up by 1 over n. But if we therefore bumped up the noise we added to f star by just 2 over n, it would continue to be the argmax. Okay? And then again, when I look at any vector of perturbations x, the probability density at x is within an e to the epsilon factor of the probability density at x plus e. So it's private. Okay. So it's a good learner in the sense that we get an accurate result, right? Like we can, if I look at the accuracy of the function actually output by this algorithm, it's within a sort of additive term that looks only like log c over n of the sort of best accuracy overall, because I can bound the error by the L infinity norm of these perturbations, which I can just bound with a union bound over the size of this class C. But the algorithm's not efficient. It had to for every function in my class, I had to come up with an independent perturbation, and then I had to take the argmax over all of these. Okay, so somehow we'd like to do a similar kind of thing, but introduce these perturbations only implicitly in a way that still allows us to prove privacy, but doesn't require enumerating the size of the class, enumerating the class that we're trying to optimize over. Okay. So here's the piece of structure that we're going to use. This is something called a universal identification set that dates back to the early days of the PAC learning literature. So for some concept class C, a collection of data points, m data points, x1 through xm, is called a universal identification set for C if for every pair of functions fi and fj in C, they label this set of endpoints differently. That is, for any fi and fj, if I look at the vector of labels that fi gives this m points, and I look at the vector of labels that fj gives these m points, they are different somewhere. No two functions in this class label all m of these points in the universal identification set the same way. Or in other words, if you tell me how a function in your class labels these m points in the universal identification set, that's enough for me to uniquely identify the function in the class. Okay, So many natural classes have universal identification sets of size equal to the ambient dimension of the space. Probably the easiest one to observe is the set of disjunctions over D features. So, like OR functions over D Boolean features. Right, so functions like this are parameterized by some set of features, and they evaluate to 1 if any of those features are 1. So if I want to read off the identity of your OR function, you just have to tell me how the D standard basis vectors are labeled. Because whenever you label the basis vector like EI1, that means that XI is in your conjunction. Okay? So this is maybe the simplest example of a universal identification set, but conjunctions and discrete linear threshold functions and parities and decision lists, these all have small universal identification sets as well, typically of size equal to the dimension. Okay, so here's the Auricle efficient learning algorithm. Okay, we're given a weighted data set, say. Okay. We're going to construct an augmented data set as follows. We just take the data set we were given. Now we're going to add to it m new elements, 1 for every element of our universal identification set. Okay? Each one, there'll be 1 for each element of the universal identification set, and the weight that we will add to that element, that thing will be drawn from a Laplace distribution with standard deviation on the order of the size of the identification set over epsilon. Okay? So if the universal identification set is small, of size D, say, we're just adding D new elements to our data set. And then all we're going to do is we're going to run our Auricle on this augmented data set. And we're going to output whatever the Auricle outputs. OK. So the claim is that this thing is private, and we can prove it with sort of the same template we used in our 2 warm-ups. OK? So pick any function f star. Imagine this is the function that's output when I ran the algorithm on dataset D. What I want to do is I want to define basically now a perturbation of the m Laplace noise random variables that I added, such that under that perturbation, coupling 2 runs of the algorithm, if I output f star on f of d, then I'll output f star on f of d prime under this coupling. Okay? So now my vector of perturbations isn't equal to the size of the concept class I'm learning over. It's just equal to the size of the universal identification set, because those are the things that we're perturbing. Okay? And the vector of perturbations will be easy to define. Basically, for every element in the universal identification set, if this should be f star. If f star labels it as a 1, then I want to perturb the random variable in that coordinate up by 1. If f star labels it as a -1, I want to perturb the variable in that coordinate down by 1. Okay. And so again, the claim is that if on dataset D for the sort of for a fixed set of weights, which includes the perturbations of the universal identification set elements we added, we output f star. Then on dataset D prime, we still output f star if each of those random variables is perturbed by this epsilon I. Okay? And the reason is, after these perturbations, f star has its score increased exactly by the size of the universal identification set, because we perturb the noise in exactly the direction that points to the value of f on that element of the universal identification set. So f had its score increased by s. But the property that universal identification sets give us is that there's no other function in our class that labels all of these points in exactly the same way. So nothing else by this perturbation could have had its score increased by more than s minus 2. Okay? And the value of these functions could have changed by at most 1 when moving to a neighboring data set, and so the gap between 2 of them could have increased by at most 2, which is counteracted by the perturbation of the noise. Okay? And then again, we observe that we've picked the right distribution so that the probability that the noise is x is bounded by an e to the epsilon multiplicative factor of the probability density on x plus e for any x. Okay. So It's an Oracle efficient learning algorithm. The error introduced is the size of the universal identification set squared over epsilon n, because we're sort of adding s many random points, but each of them is given a weight that's proportional to s as well. If you do a slightly more careful analysis with Gaussian noise, you can get this dependence on the size of the universal identification set down to s to the 1.5.
So what's the universal identification set for all the other things you mentioned earlier, like the sound procedures?
Yeah, so for conjunctions, it's like the, instead of the D standard basis.
Integer programming.
Oh, so universal identification sets are for concept classes.
Okay. So you're not, yeah.
Yeah, integer programming is maybe like the method we would use to implement, or
what?
Implement like the optimization step of the algorithm. Like at some point we need
What?
just solve the learning problem on the augmented data set. Find the conjunction that best labels the points in the augmented data set. You can write that down as an integer program. Okay, but it's like the conjunctions that have the universal identification set. Right, so like
The conjunctions on what now?
like the Boolean vectors. Like your data set, your data points are Boolean vectors. Maybe they've got labels. You'd like to find the conjunction that agrees with the labels most frequently. Okay? You fixed the class of conjunctions. That has a universal identification set of size D. But now you've got this optimization problem. You need an Oracle to solve it. Having your grad students download Gurobi is a good Oracle for that problem. Okay. So oftentimes the size of the universal identification set's on the order of the ambient dimension, and so this is suboptimal based on what we know how to do absent like Oracle efficiency, roughly by a factor of square root of the dimension. That is, I could get error d over epsilon n if I didn't care about running time.
Question.
Yeah.
So people have used like similar algorithms for contextual learning,
Yeah.
but they get like suboptimal rates. I think the best known rates are something like 2/3, and the original. Like,
Yeah, they're related. So this is closely related to sort of a technique that people use for contextual bandits. They don't get as suboptimal things because they only need closeness in total variation distance to get like the regret bound. But you're right. So this is sort of part of the.
Fast rate here. Why do you get a 1/10 rate?
Oh, we're only interested in This is measuring empirical error.
Oh, okay.
There's no The problem is very different. There's no adversary. Right.
Yeah.
But you're right. This is very similar to like algorithms known to have regret guarantees in the online learning setting. It's one of the many sort of hints that points to the fact that there might be like a much deeper connection between private learning and online learning. Okay. But privacy depends on the correctness of the Oracle. I've only got 8 minutes left, so let me quickly sketch for you how to get rid of that deficiency, how you might generically take an algorithm that has a privacy guarantee that's dependent on the Oracle, and if you have a certifiable heuristic, make the algorithm robustly private. Okay? Okay. So we want to convert, you give me an epsilon Oracle efficient differentially private algorithm. I want to get a guarantee of epsilon delta robust differential privacy. Okay. And you give me some heuristic Oracle that's certifiable. Okay, so it can fail. An adversary might be controlling when it fails, but when it fails, I know it. Okay? Okay, so first I'm going to randomly partition the data set into roughly 1/epsilon many pieces. Okay? Then I'm going to run my heuristic learning Oracle, my heuristic learning algorithm that we just saw on the previous slide, instantiated with this certifiable heuristic, roughly 1/delta many times on each of these pieces. Okay? And the privacy parameter I'm going to give it is not the privacy parameter epsilon that I want to satisfy, but crucially 1/the square root of epsilon n. Okay, so I'm giving it a different privacy parameter. I'll tell you in a moment why that's important. And one of two things could happen. Okay? It could, in one of these runs, fail. My Oracle could say, like, sorry, like, can't solve this problem. Or maybe that never happens. I'm going to remember which of those two things happened. Okay, so I'll say that this piece of the partition failed if any of these 1 over delta runs failed. Otherwise, I'll say it succeeded. Now I'm going to privately count how many of these partition elements failed by just counting how many of the partition elements failed and adding Laplace noise to it. That's just an instantiation of the Laplace mechanism, because if you change one element in the input data set, that only changes the probability of failure in one of these k partitions, because that one element only appears in one of them. So I can estimate how many of the elements failed by adding Laplace noise 1 over epsilon. And if it looks like more than half of them failed, I will halt and I'll say fail myself. Otherwise, I'm going to pick uniformly at random from the set of partition elements that succeeded. I'll run my learning algorithm with the heuristic on that partition element, again with this smaller privacy parameter, and I'll output that. That's the algorithm. OK. So first, let's observe some stuff about this. So there's a rather substantial running time overhead, OK? Because on each of these partition elements, I'm running my learning algorithm 1 over delta times. So if you want this to be polynomial time, this means you can take delta to be sort of polynomially small in the parameters you care about, but not exponentially small. Second, there's an error overhead that comes from 2 places. When we run our learning algorithms, we're not running them with the privacy parameter we want, but with this smaller parameter, 1 over the square root of epsilon n, which makes them less accurate. We're also running the algorithms not on the whole data set, but only an epsilon fraction of the data set, which also makes them less accurate. Okay, so for example, we're now going to, instead of getting error that's like d to the 1.5 over epsilon n, right, if that was the guarantee we had absent robust privacy, what you get out of this is going to look like d to the 1.5 over the square root of epsilon n. Okay, which is still, 1 over root n is sort of the rate of generalization. So if you cared about out-of-sample error, trading this 1 over n for 1 over root n maybe isn't the end of the world. OK, so let me give you a quick idea of why the algorithm works. So there's two things that might happen, right? Like the algorithm might either output fail in this step, or it might actually give you an answer. It's sort of very easy to see that the event that it outputs fail is differentially private, because it's just the result of the Laplace mechanism. We proved that was differentially private as part of our warm-up. OK? So the interesting thing is to show that it's private when it doesn't fail. So morally, like if we don't fail, 2 things are true. There's a bunch of technical details that make these things not technically true, but morally these things are true. OK? First, at least, like a lot of the partition elements actually succeeded. They didn't fail. There's, with high probability, 1 over epsilon partition elements remaining. And for all of these things that succeeded, right, they're close in total variation. The implementation of the algorithm with the heuristic Auricle is close in total variation distance to the implementation of the algorithm with the perfect Auricle, because we ran them 1 over delta times and never observed the Auricle to fail. The tricky part is that which of these partition elements survived, that's not differentially private. Like the count, the number of the ones that survived is differentially private, but which of them survived is not, because the Auricle might fail in some adversarial way. So maybe it fails if it sees my data point in there. And so which of the partition elements survived, it's not private. And so here's the kind of thing that you might worry about. OK, so let's imagine we've partitioned our data set as follows, and maybe all of these partition elements survive. OK, we've got 2 over epsilon partition elements. They all survive the first check. Maybe there's some event E, OK, that happens with high probability when I run my learning algorithm on the first partition element. Say it happens with probability close to 1. But this event E happens with probability close to 0 on all of the remaining partition elements. OK? Now the algorithm is going to pick one of these partition elements at random and run the learning algorithm on that partition element, and which means that the probability of this event E overall is epsilon over 2, because there's 2 over epsilon partition elements, and it happens when I pick element 1. On a neighboring data set, it might well be that partition element D1 is now extremely unlikely to survive the first test, which means that the probability of this event has dropped from roughly epsilon to roughly 0, which is a problem. That's not differentially private for any like non-trivial value of delta, because that's an additive change of epsilon. We need a multiplicative change. Okay? So like, we would be okay if we knew that the probability of any event E was related by some constant multiplicative factor when I ran my private learning algorithm on any two elements of my partition. Okay? Right, because if this was the case, then removing one partition element would only remove an epsilon fraction of the total mass on E, because I have at least 1 over epsilon partition elements rather than an additive epsilon. So this looks kind of like a differential privacy condition. The probability of this event should differ multiplicatively. So does differential privacy just give us this? And the answer is no, because differential privacy promises this for neighboring data sets, di and dj, that differ in one element. But these are entirely disjoint. So we don't have the differential privacy guarantee. But there is something we know, which is that both of these things, both di and dj, were drawn from the same distribution. Okay, because they resulted from a random partition of the data set. And it turns out that differential privacy gives you this kind of guarantee, this kind of multiplicative change in events for two data sets that are drawn from the same distribution when the privacy parameter is on the order of 1 over the square root of the size of the data set. Essentially because the log probability density function is epsilon Lipschitz, and you can apply something like McDermott's inequality. Okay. So that's why epsilon had to be smaller. Okay. So okay, I'm out of time, so I'll talk about the barrier result with, you know, those of you who are interested offline. It's reducing, it's sort of, just to say something about it, it follows from the observation that there's a large class of differentially private algorithms that includes everything we've given in this paper that are known to be no-regret learning algorithms. And Elad and Tomer Koren have shown that there's a separation between Auricle-efficient online learning and online learning. Okay? And so basically, applying that to our case means that if you were going to get an Auricle-efficient learning algorithm that had sample complexity for any class within polynomial factors of what you would be able to do without Auricle efficiency, it would have to be with an algorithm that couldn't be converted in an Auricle-efficient manner, at least, to an online learning algorithm. We don't know if there are any such things. That's an interesting open question. Okay. So that's it. There's a bunch of open questions. Basically, the reductions we give have some error overhead. We don't know the extent to which that's necessary. They've got some running time overhead. We don't know the extent to which that's necessary. We require these sort of certifiable oracles. Hard to imagine how to get rid of that, but maybe you can with some other condition. And we use this relatively heavy structure of universal identification sets, which in particular limits us only to discrete classes of functions. But there might be more general structure that one can use, and in particular it could be that everything that's privately learnable is privately learnable in an Auricle efficient way. And so thank you for listening. Happy to take questions. I know, and while I've got like an audience, shameless book plug, my colleague Michael Kearns and I have written what is basically a popular science book, but has, you know, like a chapter on differential privacy in it, a chapter on fairness. It's coming out in the fall, and maybe some of you guys will be interested. So thank you. Yes.